Free Calculus. We are on Chapter 10, Section 2, and we're going to be studying the next area of calculus. In Section 1, we learned about derivatives, rate of change, and we used a limit formula to figure out a derivative. Example 1, computing distance traveled. An automobile travels at a constant rate of 48 miles for 2 hours and 30 minutes. How far does the automobile travel? Well, we know distance equals rate times time, so I should be able to multiply my rate times my time and figure out we went 120 miles. Well, let's see if we can't use a graph to help us get the same answer like we used a graph in Section 1 to help us understand rate of change, what we were doing when we were finding derivatives. So if we look at a graph where we make our x-axis the time, so this will be our t-axis, and let's make our y-axis the rate, so how fast we are going. So if I am going at a constant 48 miles an hour, so there's a constant rate of 48 miles an hour, and we do it for 2.5 hours, when I connect that, I get a region underneath this curve that is a rectangle, and we find a rectangle by using the same formula that we did a minute ago to get distance. We multiply these two values together. The area is going to be length times my width, and so if I'm going to call my length, I'll do it the same order and call my length 48 and my width my 2.5. Well, the area under that curve is 120. So this is the idea that we are going to be working at, finding areas under curves. And in this instance, the area under a distance versus time curve, or a rate versus time curve, would give us the distance traveled. Distance question. Suppose a ball rolls down a ramp, just like in Section 1. We have this ramp, ball starts at the top, rolls down the ramp. If its velocity is always 2t feet per second, so this ball is a special one, it's not accelerating. It is accelerating. Its velocity is always 2 times the time. As our time gets bigger, longer, then our velocity gets bigger. After 1 second, it's just 2 feet per second. After 2 seconds, we're up to 4 feet per second, etc. So t is the number of seconds after we have started rolling. It wants to know how far does it travel during the first 3 seconds. When we had one velocity, we were able to just say the velocity times the time, or the rate times the time. But we don't have one velocity. It is changing. It's changing with the equation 2t. 0 seconds, 2 times 0 is 0. It's not moving at all. After 1 second, we're moving 2. After 2 seconds, 4. After 3 seconds, 6, etc. So we're changing the speed. Well, let's see if we can do the same idea with a graph that we did a minute ago. We're going to have a rate versus time graph. And our rate equation is this 2t. So r equals 2t. That is a linear equation. The y-intercept, just like y equals mx plus b, the y-intercept is 0, right down here. Don't have a y-intercept. Our slope is 2. Slope is 2. So rise 2, run of 1. So rise 2, run 1, rise 2, run 1, something like this. So we have this rate going like that. And we want to continue this for 3 seconds. 1, 2, 3. We want to continue it for 3 seconds. So if I connect my 3, the area under the curve should give us distance traveled if it works just like the last time. Well, what's my shape? My shape's a triangle. How do we get the area of a triangle? We get the area of a triangle 1/2 base times height. So let's figure out the area of that triangle. 1/2, the base of this triangle is 3. The height of this triangle, well, what's my height at that location? Well, after 3 seconds, 2 times 3, since this is giving me my r value, 2 times 3 is 6. My height must be 6 right there, times 6. Well, half of 6 is 3. 3 times 3 is 9. 9. We must have gone a total of 9 feet. So we were able to use the area under the curve, and it was a shape that we knew for our area under our curve. We called our equations, when we graph them, curves, even though that's a straight line. We still call it a curve, the area under that curve, the area under that equation. Happened to be 9 feet, from 0 seconds up to 3 seconds. We talked about a limit last time we met, where we were approaching a value. What does the equation approach as our x value approaches a value? Well, we want to know the limit when we're going to infinity. So let's talk about that a little bit. Some function, the limit of a function as our x value approaches infinity approaches L. So our function answer, our function value gets closer and closer to L as our x gets bigger and bigger and bigger and bigger. So let's see if we can have an idea of this infinite limit, see what happens to it. Let's look at this little exploration. A gallon of water is divided equally, poured into teacups. Find the amount in each teacup and the total amount in all the teacups. If number 1, we have 10 teacups. Well, if I have 10 teacups, how much is in each teacup? Well, it'll be 1/10, because I take that 1 gallon and I divide it all out. We have a gallon of water, 1 gallon of water, divided into 10 teacups. So it'd be 1/10. And then how much is in the total? Well, I add all those 1/10ths together, and I should have 1 gallon when I am done. Probably can see it right over there. 100 teacups. Pretty easy to figure out. I'd have 1/100th of a gallon in each teacup, and when I add those 100 1/100ths together, I have 1 gallon when I'm done. What if I had 1 billion teacups? Well, not much in each teacup, but there's 1/100000th in each teacup. And if I add those 1/100000ths of a gallon together, I end up with 1 gallon when I am all done. Now try this one. An infinite number of teacups. Can you figure out, if I have an infinite number of teacups, how much would I have in each teacup? Maybe the second question will be easier. If I add all those teacups together, what should it add to? Well, it should add to 1 gallon when I'm all done. No matter what amount I have in each teacup, if I take my water and divide it all up evenly, and then put it all back together again, I've got 1 gallon. Well, the interesting thing is when I divide up something infinitely, each piece, there are 0 gallons per teacup. We'll uncover it. There are 0 gallons in each teacup when I divide it up infinitely, but yet when I add all those together, I get my gallon back. You can philosophize about that for a little bit, maybe. Let's look at this idea. The limit. This is what we have been doing. We have in amount of water, in gallons of water. Or I shouldn't say in gallons of water, we have in teacups. So in each teacup, I have 1/n amount of water. And then if I multiplied it by the number of teacups I have, I should be back to my 1. Because n times 1/n, well, n/n is just 1. Even if I limit that n to infinity, no matter what number I put in there, then I should have that same answer. Now, how much is in each teacup? Well, when we take n to infinity of 1/n, we get 0. We've seen that before. This number keeps getting smaller and smaller and smaller. 2 teacups, 3 teacups, 4 teacups. This number keeps getting smaller and smaller and smaller, and it limits to 0. We have 0 in each teacup. I don't know if you're convinced yet that we can have 0 in each teacup and add them all back together and we have a gallon, but mathematically that's what we need to believe at least. Okay, so back to this, connecting our areas again. We can get our distance of 120 miles by figuring out the area under this curve of a velocity or rate versus time graph. Area under the curve was nice and easy on this because it was a rectangle, length times width. Area under the curve of that triangle was easy because we know a nice formula for a triangle. But what if my velocity is changing? What if I'm not this constant rate of velocity? So I have a velocity that's speeding up, and then my velocity slows down again. How can I get the area under this curve? And this time we're not even starting at 0. We're going to start at some other value, a, and we're going to end at this value. So maybe it's between the 5th and 12th seconds or something like that. How can I get the area under that curve? Well, what if I divided up this region into little pieces? So that's what we're doing here. We're just dividing it up into little pieces. And if I look at those little pieces, they kind of look like little rectangles, except the top of those rectangles are not flat. So I could estimate it if I took the right side of the rectangle and came back to square it off. The right side came back and squared it off. And I did that each time. Now there it's pretty close. There it's pretty close. Right side of the rectangle, I'm actually a little smaller now. You notice that's a little less. And then if I found the area of each of these rectangles and added them together, I would be close to the region under the curve or the area under the curve. I wouldn't be exactly right. Here I'm a little bit too large. My areas are a little big. But over here, my areas are a little small. So maybe it will average out to be fairly close. When we take the right-hand side and draw rectangles, it's called the right rectangular approximation method. So here they have given us the function x squared. It's a parabola. Here we have this parabola. We want to find the area under the curve using 6 rectangles on the interval from 0 to 3. On the interval from 0 up to 3. So we're trying to find the area under the curve in this region right over here. And we're going to use that right rectangular method, dividing up into 6 parts. And we'll find the area of each of these rectangles, real small one to start with, each of these rectangles. And again, we're taking the right side and we're making our rectangle with it. Well, let's start at the beginning, right back here. Take the right side, we make our rectangle with it. We've got a real small rectangle right there on the interval between 0 and 1/2, because 0 to 3 into 6 pieces, each one is a half a unit wide. Well, I know how wide it is, it's a half. And I know to find areas of rectangles, we multiply our length times width, or base times height together. So my base is a half wide. And what is my height? Well, my height is what's the value of the function at a half. I put a half into the equation. Well, the equation is to square it. A half squared is a fourth, so it's a fourth. So it's a half by a fourth. There's the area of the first one. And we can continue to do it. My next rectangle, it's also 1/2 wide, so the base is 1/2. And the height of it, well, you put a 1 in. You square a 1, and you get 1. So it's a half by 1. A half times 1, there's the area. And you keep doing this for all 6 rectangles. You add them all together, and you get this value. Total area. Now, do you think this estimated area is too big or too small? Okay, hopefully you said too big, because we have all these extra parts to the rectangle that we're adding in there. So that one's just a little bit too big. So that 11.375 is a little bit larger than we really wanted. Well, if I did, here is our 11.375 from the right rectangular approximation method. What if I used the same idea, but I did a left rectangular approximation method? In other words, I took the left side of the graph and made that my top of the rectangle and found the area from this one. again between 0 and 3, dividing it up into 6 parts. If we did that using the same process as before, this is the value we would get. Well, this value is just a little bit too small, but our first value is a little bit too large. So what if we took the average of those two values? If we took our 11.375 and our 6.875 and found the average of those two values, we'd get 9.125. So what about that? Well, that's probably closer. It's probably pretty close to the real area. And if we divided it up into more rectangles, if I have more rectangles, then I am more accurate with it because I have smaller and smaller pieces that I am either missing or I am adding. So the more rectangles I make, the more accurate I can be. In fact, I say if you happen to do 20 rectangles, you would get this value for the area under the curve. It looks like we're getting close to a certain number. In fact, the actual area is 9. And we can see as we're getting more and more rectangles, I'm getting closer and closer to that number 9. So what do we do with the idea in calculus to get area under curves? Well, let's see. Remember, this means the summation. I'm going to take the sum. I'm adding up all these rectangles. I'm going to take the sum of the, now f of x sub I starts at 1, our first rectangle, our second, our third, up to n, however many rectangles we want to make. This would be the height of the rectangle. Delta x, that's the base of the rectangle. F of x, right there, that is the height, f of x, the value of the function at x of 3. And how wide is it? Well, that's my delta x, how far it is between all my x's that I'm choosing. And so this really just means we are taking the sum, or it's the summation of all rectangle areas. And we saw a minute ago that the more rectangles that I make, the closer and closer I get to the true value. So can I do an infinite number of rectangles? Let's go to our definition box. In calculus, it's called an integral. In fact, it's a definite integral when we have two numbers that we're trying to find an area between, or an area under. We were going between 0 and 3. So this is a definite integral. When I integrate in calculus, I find the area under a curve to the x-axis. So they're saying here, we have some function, and it's defined on this interval from a to b. Then, the summation of all those rectangles that we make, that's what we saw right over here. We're just adding up all those little rectangles. Like we were talking about above, is called the definite integral over the region from a to b. And this is the notation we use. I should change it right over here. It looks like a stretched out S between A and B. Those are the values we're going between of a function. So there's some sort of an equation we're using. Our equation was x squared with respect to x. Remember that little dx? When we were talking about derivatives, we said the derivative of a function, y, and we might write the equation, with respect to x. There's that same notation. We're integrating an equation with respect to x. So this is a definite integral. And what is that definite integral? Here's that notation. What does it mean? It means we're doing this. As long we have an answer to that, as long as we say it's integrable, long as we can do it. All the ones we're going to see right now we can do. We're not going to run into non-integrable equations. So the idea again is we are finding the sum of all the rectangles. And how many rectangles are we going to do? We want to do an infinite number of rectangles. And if you think about that, how wide is each rectangle? Well, the width of each rectangle is actually 0. But we have a definite height for it. But when we add up all those rectangles, even with width 0, we get the total amount under that curve. Just like those teacups, infinite number of teacups, when I take my gallon and divide it up an infinite number of times, there may be 0 in each teacup, but when I add them all together, I get my 1 gallon back. I guess you'll just have to believe it. Okay, so let's try it. They want us to find the definite integral of 2x between 1 and 5. Well, right now, all we know how to do is we're finding the area under the curve, under this 2x graph, between it and the x-axis, between the numbers 1 and 5. Well, 2x, we graphed it a minute ago. That's just that line. Y-intercept is 0, slope is 2, so there's our line. And we want to find the area under it between 1 and 5, right over here. We're trying to find this area. Since we know no calculus rules yet, we just have to find the area of that geometric shape. Well, that shape's a trapezoid. You may remember that from geometry. We have exactly one pair, 2 parallel sides, and then the other 2 sides that are not parallel. We have a trapezoid here. The area of a trapezoid, if you recall, is 1/2 the height times base 1 plus base 2. So let's see if we can figure that out. Now the height is the distance between our parallel sides for a trapezoid, so that would be defined as our height on this trapezoid. So 1/2 our height. Well, our height is 4. We're a distance of 4 between those 2 parallel bases. The length of each base. Well, if I called that base 1, we're going to need to figure out what that is. If I call that base 2, we'll have to figure out what that is. And how do we figure out that length of the base? Well, it's the value of the function at 1. When I substitute a 1 there, what do I get? 2 times 1 is 2. It's too high right there. And over here at 5, substitute a 5 in my equation. 2 times 5 is 10. It's 10 high right over there. So one base is 2, the other base is 10. Half of 4 is 2. 2 plus 10 is 12. 2 times 12 is 24. There's the answer to this problem. The definite integral of 2x with respect to x between 1 and 5 is 24. That's the area underneath that curve. So let's go back to this initial thing where they're talking about this ball rolling down a ramp. So its velocity after t seconds is always 2t feet. How far does the ball roll during the first 3 seconds? If I'm using my calculus notation, I'd say, oh, that is the definite integral between 0 and 3, our first 3 seconds, 0 to 3, of our equation 2t with respect to t. Notice our variable is t instead of x, so it's d of t with respect to t. Now, we have our velocity equation, 2t. We've been graphing that several times. There's our velocity equation, 2t. And we want to go between 0 and 3. We did this way at the beginning. This is just a triangle. And so we know the area under triangle, 1/2 base times height. 1/2, my base is 3. My height, 2 times 3. 2t is our equation. Our time is 3. Is 6. Our height is 6. We still get a 9. We have traveled 9 feet. Now, let's pull out our calculators. So get your calculator all turned on. And let's enter this equation, 2t. Well, I can't enter, if you have a plot on, turn any plot off, make sure you're in function form there. I can't do 2t, I can do 2x, so my variable 2x. And let's go ahead and look at that graph. Zoom, standard, just going to do a standard graph. So there comes my line. We want to find the area under this between 0 and 3. Use your calculate up here under the graph above the trace. Second, calculate. And arrow down to choice number 7. And guess what you see? The integral of f of x with respect to x. We want to integrate this equation. So I'm going to say enter. Lower limit, where are we starting? We're starting at 0. Lower limit, enter. Upper limit, how far are we going? We're going to 3. Upper limit 3, enter. It draws it out, and not only does it draw it out, but you can see a nice little answer underneath. See if I can't capture that page. They say, when I integrated that, I got 9. So your calculators know how to integrate those equations. Pretty nifty. Now, kind of short what we have right here, not too long. When I come back, I'm going to talk more about what our calculators can do, as well as give you a sheet with some derivative rules. And so we're going to learn some derivative and some integration rules where we don't have to go to this geometry to get area under curves when it's only a shape that we know a geometry formula for, but we'll be able to get area under curves of any shape. All right, you can use your syllabus and you know the assignment, and I'll see you guys when I get back.